All right, section 1.5 is on solving inequalities. Inequalities when you get the less than, greater than, less than, equal to, greater than or equal to. So we're going to solve some inequalities and graph them, and then we're going to write and solve what's called compound inequalities. When you've got more than one number involved, you're saying like 2 is less than some number, and that number is less than x. So you're comparing some variable to two boundaries, so to speak, instead of one. That's compound. So first problem. What inequality represents a sentence 5 fewer than a number is at least 12? It starts off 5 fewer than a number. Quite often when I'm doing these problems, I look for the word is, because it kind of is a divider, and then is means equals in math, but is at least means something other than equals. Is at least, well, if I have at least $10, that means I have 10 or more. So is at least is actually greater than or equal to. So right there, that symbol is going to go there. 5 fewer than a number, that's 5 fewer than some number, we'll call it x. How do I do 5 fewer than, say, 6? Well, 5 fewer than 6 is 1. Because 6 minus 5 is 1. So we nearly need to write x minus 5. A lot of times we go straight forward from left to right, we'd write the 5 first. But because it says fewer than, we actually need to put the minus 5 at the end. Is at least 12, greater than or equal to 12. Add 5 to both sides, you get x is greater than or equal to 17. And that's all we needed to do on there was write an inequality. Well, actually, we didn't need to solve it. So I got ahead of us there. So that's all you would solve, just add over the 5. But the inequality is this part right here. Okay? What is the solution of? Graph the solution. Okay, well, now we're just going to solve this inequality first. It's just like solving an equation. If I told you to solve this, you could do one of two things. You could distribute first, add like terms, isolate the x, or you could get the parentheses alone first and then isolate the x. So kind of up to you. We talked about this in a previous section. So whatever you feel like doing. I guess I'll subtract the 1 and get 3. I could distribute the negative 3, but I see right now that if I actually divide by negative 3, that it'll go evenly, nicely into the other side. Now I'll be left with 2x minus 5 is greater, whoop, careful. I was going to say greater than, but what I forgot there for a second is I'm dividing by a negative. And that's where you got to be real careful here. When you multiply or divide both sides by a negative, you need to switch the inequality symbol. So it's less than or equal to negative 1. Example of that, here's a true statement. 8 is greater than negative 2. This is totally unrelated to the problem we're doing right now. 8 is greater than negative 2. If I multiply both sides by negative 1, I get a negative 8 on the left and a 2 on the right. Well, if I leave the symbol the way it is, it's not a true statement. I need to reverse it. I need to make it a less than, and then it remains a true statement because negative 8 is smaller than 2. We always point at the smaller number. Okay, so there's a reminder of why you switch the symbol. Now we continue over here. I'd add 5. Get 2x is less than or equal to 4. Negative 1 plus 5 is 4. And then I would divide by 2. Get x is less than or equal to 2. So any number less than or equal to 2 is a solution to this problem. Now this represents all our solutions. This is our answer. But if I said, list 3 solutions, you could say 2, you could say 1 and 0. You could say negative 10. You could say 1 1/4. Anything that's less than or equal to 2. How do we graph the solution? Well, all we do is put a number line down, and I'm simply going to have you put down the boundary number, which is our 2. And decide what kind of circle to put above it. Now, the circle is based on the symbol. Now, here we have a less than or equal to. So a less than or equal to means I want 2 to be included in my answer. So to show that 2 is included in my answer, I fill a circle. That's for less than equal to or greater than equal to. If it was just a less than, I'd leave it open because I wouldn't want 2 to be an answer. We're shading things that work, so that's why I need to shade the circle to show that 2 would be an answer because 2 is less than or equal to 2. What else works? Anything to the left of 2. 1 is less than 2, 0 is less than 2, negative 1 is less than 2, so we're just going to shade all the way to the left. that represents a graph of our answers. Movie rental company offers 2 subscription plans. You can pay $36 a month and rent as many movies as desired, or you can pay $15 a month and $1.50 to rent each movie. So there's 2 things. There's $36 a month, and the other thing is $15 a month and $1.50 for each movie. So if I was that person, I would give them $15, but I would have to add $1.50 for every movie that I rent. So if I rented 1 movie, it'd be $16.50. If I rented 2 movies, it'd be $1.50 times 2, 3, plus 15, $18. That would be for the month. So how many movies must you rent a month for the first plan to cost less? So our first plan was just 36. There was no variable there. It's a flat rate of 36, and I want that to be less. I want this to be smaller. I want 36 to be a smaller number. So there's my setup. Now I get to solve, minus the 15 over, I get 21. And then divide by $1.50, 21 divided by 1.5. 21 divided by 1.5 is 14. So if you want to make the first one the way to go, you need to rent over 14. You need the number of movies, count as movies, to be greater than 14. If it was 14, that would mean they're exactly the same, and it doesn't matter. But 14 is the magic number. Over 14. Over 14 movies. If you have a word problem, it's nice to answer the word problem with units and in words, and not just give me a number, so we can see that you understand what's going on. Is the inequality always, sometimes, or never true? Well, this goes with our equations that we did in 1-4. Apparently, x might drop out. So if x drops out, we're going to have an always or never, just like we did with the equations. Sometimes if x doesn't drop out. So here, I guess I'd be inclined to distribute on the left to get negative 6x minus 2 is greater than negative 6x plus 7. Now, if I get the x's on the same side, I'm going to add 6x to both sides. They cancel out. And I'm left with negative 2 is greater than 7. And I just need to ask myself, is negative 2 greater than 7? Well, no. 7 is greater than negative 2. Negative 2 is not greater than 7. So I have a false statement. And just like with the equations, when you have a false statement, it's never true. There's no x you're going to be able to plug in there to get it to work out. It would be like saying someone has a $2 debt and they lose $6 a day. Someone has $7 in their pocket and they lose $6 a day. When's that first person going to be bigger? Well, never. They start off lower and they're losing the same amount every day. So that's a never situation. If it was true, you would put always, and if the x's didn't drop out, you would put sometimes. Okay, here's our compound inequalities where you've got x compared to 2 different things. This compound inequality is separated out into 2 separate problems. You just solve them. I'll solve this one on the left here. I'll minus the 1. I get 6 is less than 2x. I'll divide the 2 and get 3 is less than x. And what's important on these guys is to recognize if it's and or. And this one has an and. Include that in your answer. If it says or, put or in your answer. If it says and, put and in your answer. So I got an and. Now I'm going to go ahead and solve the other inequality by dividing the 3 over, and I get x is less than or equal to 6. So the number I want is greater than 3, and it's less than or equal to 6. Number I want, so now I have 2 boundaries. I have 3 and I have 6. What kind of circles am I going to deal with here? Well, with the 3 it can't equal, so it's going to be an open circle. And with the 6 it can equal, so it's going to be a closed circle. And these ones that say and, what that implies is you're always going to be shading in between. Okay? You're finding numbers that work for both. Like there's an infinite amount of numbers that are greater than 3. In fact, there's an infinite amount of numbers that are greater than 3, but they're not less than 6. Like if I said x, the x over here, right here, could be 10. But x over here couldn't be 10. So we're shading the numbers that work for both this and this. It has to work for both of them. So we shade in between. And is generally shaded between, or when it says or more times is not, it's going to be shade out to the left and right. Not always, but quite often. Here we have that or problem. Just write that in my answer, or. And I'll solve the left and I'll solve the right. On the left, I subtract 7, so I get k is greater than or equal to -1. On the right, I subtract 8, so k is less than -5. There was no reason to switch any symbol here. I didn't divide or multiply both sides by a negative. So here, when it's or, it doesn't have to fit both descriptions. Your answers can coexist. It's like if I said, when is H2O not a liquid? Well, when it's freezing below 32 degrees Fahrenheit, or when it's boiling, when it's above 212 degrees Fahrenheit. So we're going to have two possibilities. And my left possibility is -5, that's my small boundary. -5 is smaller than -1, and I'll put my -1 on the right. -5 doesn't have an equals, just a less than, so it's going to be an open circle. And which numbers are less than -5? Everything to the left. -6, -7, -8, and so on and so forth. -1, that one has an equal, so I have to say -1 can work, so I have to shade it. And which numbers are greater than -1? Everything to the right. And more times than not, this is how your order problems are going to look, where you've got shading to the left and shading to the right. Okay, not always, but quite often. Okay, solve for x. Here's another compound inequality. This is another way to write an and problem. I could have wrote that and problem before just like this, because it's just showing that x is between two numbers. So I shouldn't say always, but again, most times when it's and, you've got x between two numbers. I could show you an example where it's not in between, but we're going to be pretty much focused on in between. So all you do here is subtract the 5, get the x one, but you subtract it on the right and the left. Like I'm saying, you could write this as 3 is less than 2x plus 5, and 2x plus 5 is less than or equal to 11. You could write it as two separate problems. Your call. When it's in this form, I like to leave it as is. So I get -2 is less than 2x, is less than or equal to 6. Divide both sides by 2, and I get -1 is less than x, is less than or equal to 3. Some people make a mistake right here because they see that negative, they think they'd have to switch the symbol. But you don't have to switch that symbol because you're not dividing by a negative. You're dividing by a +2, so the symbol stays the way it is. And x is going to be in between these two numbers. -1 smaller, put it on the left. 3 is bigger, put it on the right. Open circle above -1 because it doesn't have an equals underneath it. There's no equals right here. Closed above the 3 because it does have an equals right there. It's got that little equal symbol. And x is anything in between these shaded between. You notice the first ones I put on the number line, and the second ones I put above the number line. Whatever works for you, you can either put them on the number line or above it. I've seen both ways, it doesn't matter to me. And that is our lesson for the day. Thanks for watching. Have a great day.